So here we are, the dreaded Standard 16. In Standard 16, we'll be talking about stoichiometry, which is really the math of chemistry. And really, if you stick with it and pay very close attention to what we do, it's not actually all that bad. Don't buy into the hype, it's actually pretty easy. So let's get to looking at it. Stoichiometry is no more difficult than making a breakfast sandwich. Now, I'm going to be honest, breakfast sandwiches are one of my favorite things on the entire planet, especially bacon, egg, and cheese bagels. So in order to make a breakfast sandwich, you have to first have some bacon, some eggs, some cheese, and a bagel. Okay? And how much bacon and eggs and cheese you put on your bagel is really up to you, but my preferred sort of strategy is to take 3 strips of bacon, 2 eggs, 2 slices of cheese, and 1 bagel, piece it all together, and you get some magic. Okay? So if we were to turn this into a chemical equation, okay, to represent what we just did with a chemical equation, I'm picking some abbreviations like BN for bacon, EG for egg, CH would be cheese, and BG for bagel. We said 3 strips of bacon, 2 eggs, 2 slices of cheese, and 1 bagel are required to make 1 bacon, egg, and cheese bagel. Okay? And the bacon, egg, and cheese bagel will have subscripts based on how many different things are actually in that final product. So we use 3 strips of bacon. There are 3 strips of bacon on our bagel. 2 eggs are in our bagel. We've got 2 slices of cheese in the bagel and also the bagel itself. And if we wanted to double the recipe, all we would simply do is double the number of ingredients we use. Use 6 strips of bacon, 4 eggs, 4 slices of cheese, 2 bagels, and you would wind up with 2 bacon, egg, and cheese bagels that are identical to each other. Stoichiometry is no more difficult than that. The only difference is that instead of making bagels, we're dealing with chemistry, chemical reactions. So if we look at the reaction for the synthesis of water from hydrogen and oxygen, which is probably one of the easiest for us to really describe, to get into for figuring out chemical equations, we said that in order to balance a chemical equation, you had to pay very close attention to the coefficients, so that in the beginning you have the same atoms that you end with. Like in the synthesis of water, since oxygen is diatomic, it comes in 2s, we need 2 water molecules to account for both of these oxygens. Which means that we need a total of 4 hydrogen atoms in the beginning, and since hydrogen is also diatomic, we need 2 hydrogen molecules. And that works on the molecular level, okay, adding up these molecules. It also works on the level of mass, atomic mass. So if we look at the atomic mass in the beginning and in the end, it should add up to be exactly the same. And also we can scale this up to not just talking about 1 atom or 1 molecule at a time, but talking about moles. 2 moles of hydrogen, or 600 sextillion hydrogen molecules, or really that'd be 1200 sextillion, plus 600 sextillion oxygen molecules would give us 1200 or 2 times 6 times 10 to the 23rd water molecules. And the same thing once again works with grams. Okay? And so using this, it's as if Mole Island, so going back to our Mole Island diagram, is about to expand. Imagine that you're standing on Mole Island. You've got your trade network established with the particles, with the liters, and with the grams. But suddenly you're standing on Mole Island and you notice a wormhole open to another dimension. And in that other dimension, the other Mole Island appears. You can see the Mole Island that you're standing on, except everything looks just a little bit different. In fact, everything looks reflected. And so when we use the Mole Island diagram, we've been describing your trade network between Mole Island and mass island, volume, and particles. But now we're about to add more to it. In that, we can change the known amount of one substance in a reaction and use it to either predict how much we need, or to calculate how much we need, or predict how much product we will get of another substance. And in order to do that, we need these coefficients from the balanced chemical equation. So when in doubt, always convert things into moles. Also, since Mole Island, this is a reflection of the island that we have, if you remember, going from left to right on Mole Island causes us to divide. So to go from mass to moles, we have to divide by the molar mass. But since this other alternate dimension Mole Island is a mirror image of the one you're standing on, you're going to do the opposite once you get to the next set of moles. So to go from moles to mass, to go from left to right, is to multiply. So let's say in our chemical equation that we were looking at before, the synthesis of water, you wanted to make 6 moles of water. The question is then, how many moles of oxygen will you need? So once again, looking at our balanced chemical equation, we know that there are 2 moles of hydrogen come together with 1 mole of oxygen to make 2 moles of water. So there are 2 approaches to this that you can take, and either one is totally fine, and it'll work every single time. I definitely have the one that I prefer, but some of you may prefer to do things in terms of cross multiplication and setting up ratios, which will totally work. So if you want to take 6 moles of water and relate it to the number of moles of oxygen you will need, all you have to do is look at the ratio of those coefficients. You know that 2 moles of water require 1 mole of oxygen. So we can scale that up. We can say 1 mole of oxygen creates 2 moles of water. So then how many moles of oxygen will we need to produce 6 moles of water? And here you can do your favorite strategy to cross multiply, or you can think about this like a series of ratios, of conversion factors. Okay, so for example, if we have 2 moles of hydrogen, that tells us we need 1 mole of oxygen. Or flip that on its head, 1 mole of oxygen to 2 moles of hydrogen. And really, even though we only have 3 things in this reaction, we can build 6 different conversion factors. But the simpler way to think about this is to simply say, well, since you have 6 moles of water, you want to multiply it by some conversion factor that has moles of water on the bottom. And we can relate the 2 moles of water in the balanced equation to the 1 mole of oxygen. And we can set up our conversion factor just like we've done with other things. But part of the problem is that we can't really measure things in moles. All right, we don't have any equipment in the lab that uses moles. Instead, 99% of the time we're going to be using grams because scales are easy to use. Okay? And so when we do this, we then have to convert our moles into grams. So we have to look at our grams of water, our grams of oxygen. And so we ask a slightly different question. We can say, using the same balance equation, we can ask the question, if you have 64 grams of oxygen, how many grams of hydrogen would you need in order to complete this reaction? And to answer this is as simple as reading the mole island diagram like we've done in the past. The only difference is that now, instead of converting within the same substance, we're converting between 2 different substances. Okay? So if we look at where we start with 64 grams of oxygen, which puts us on the mass island of our known substance, the thing that we're given. We know how much oxygen we have, so that's our known substance. And we want to convert that into grams of hydrogen, our unknown substance. So in order to do that, we have to go over to our mass island of the second substance we're dealing with, in this case hydrogen. Since hydrogen is not the same thing as oxygen, we have to convert into a different set. So to do this, we notice, if you add it up, you take 3 steps. You first have to go from mass of oxygen to the moles of oxygen, then convert to moles of hydrogen. Okay, now we're in the parallel universe, and then you can convert into the mass of hydrogen. So once you plot out your steps, you notice you've got to do 3 things. There are 3 jumps. Okay, and the first jump is to go from mass of oxygen to moles of oxygen, just like we've done in the past. So setting up a conversion factor, I can say, well, 64 grams of oxygen is what I have. Multiply it by some factor where grams of oxygen would be at the bottom. And it says here that I have to use my molar mass, and my molar mass is equal to 1 mole. So my molar mass of oxygen, since oxygen is diatomic, we have to multiply the mass on the table by 2, which gives us 32 grams per mole. So 64 times 1 divided by 32 tells us that we have 2 moles of oxygen. From there, we're now on Mole Island, and we need to hop over into the parallel universe of hydrogen, the moles of hydrogen. To do that, we need to use our balanced chemical equation. So just like we were looking at before, you can use cross multiplication, or you can set up a ratio. I did the ratio here, but cross multiplication will still work. In that, so you take your 2 moles of oxygen that you have, that's where you're at on oxygen's mole island, and you can multiply it by some conversion factor where moles of oxygen will be on the bottom and moles of hydrogen will be on the top. And to figure out that relationship, we look at the coefficients of the balanced chemical equation. So we know that 1 mole of oxygen, and remember we don't see a number here, there's no coefficient, which means it's 1, is related as uses 2 moles of hydrogen. Okay, so 1 mole of oxygen, 2 moles of hydrogen, so we take 2 times 2 divided by 1, tells us we would need 4 moles of oxygen in order to react with 2 moles of oxygen. Once we know how many moles of hydrogen we need, we then simply convert into the mass. Once again, you can just multiply by the molar mass since we're going from moles to mass. Or you can set up your conversion factor again and say, well, if we have 4 moles of hydrogen, we can multiply that by 2 since hydrogen is diatomic. It has 2 grams per mole, so watch out for that. There are 2 hydrogens in each molecule, so 2 grams per mole. So the mole unit would eliminate, and the only unit we'd be left with is grams. And so we take our 4 times 2 divided by 1 would be 8 grams. And so to answer our initial question, if we have 64 grams of oxygen, how many grams of hydrogen do you need? We would simply say we need 8 grams. And Mole Island doesn't get any harder than this. This is all of stoichiometry, and really this is just about all there is. The only difference is that sometimes you might not be using mass, or you might stop at moles, or you might even be given the moles of one substance and have to convert into mass or volume or even moles of another substance. The only difference, the only trick is to know where you start, where you're going, and the steps that you need to get there. And that's all there is to it.